Today we're going to we've got a guest speaker, Nicholas Francoeur from Tech Resources, who's going to talk to us about this GR4J precipitation runoff model that has been developed that he developed in GoldSim, and I'll go ahead and just turn the time over now, and at the end of the presentation, we will have some time to field some questions if you have any.
Okay. Thank you, Jason. So, yes, my name is Nicholas Francoeur. I work for Tech Resources, most particularly in the steelmaking coal business unit. Most of the operations are located in the Elk Valley in southeast British Columbia, which you have a beautiful picture here. So just before we start, I'm just going to go through my slide deck is not responding. Okay, it is now. Just go to quick safety share. The winter is upon us in the Canadian Rocky Mountains. I understand that most people in the second presentation of the day are listening from Australia, but this topic is still valid in difficult road conditions. If it's raining, thunderstorms, most of us will use cruise control. It's a very convenient function in a car. You should not use it during difficult road conditions because your car always try to maintain the same speed, and you don't have your foot on the pedal. So it's a really good recipe to find yourself in the ditch. So please avoid using that function when road conditions are difficult. So my background is mostly mine water balance models, but the model I'm going to be presenting today is applicable to for other purposes, such as water supply for domestic use in the reservoir, various catchments for irrigation purposes, for instance. But most of my topic will revolve around mine water balance models today. So yeah, so what do you expect from a good mine water balance model is a good runoff, precipitation runoff processor. And what characterizes such a good processor is precision and accuracy. So the capacity to replicate a river hydrograph, but also to limit the bias that in the end you model the same cumulative volume than what's being measured. You want a robust model so that it's valid across several hydrological regime and season. Universality, so obviously there are mines in the northern Canada, in Australia, all around the world. So you want a model that is valid in different geographical locations and morphology. A really important point is parsimony. So you want few and readily available input variables to your model, and you want a few free parameters, those that you change for calibration, to prevent equifinality. So equifinality is getting to the same result with a different set of parameterization. Obviously, you're going to be simulating a whole bunch of catchments simultaneously, so you want computational speed. And then, although the name precipitation runoff model implies that there's basically two processes of the hydrological cycle, which is precipitation and runoff, we're actually interested in more than that. The actual evapotranspiration is important if, for instance, you're developing a remediation over your waste dump that will promote evaporation to limit percolation within your dump. Then you want to be able to express that in your model. And the same goes for groundwater. If you have an open pit or a dam that is basically obviously always seeping a little bit, you want to be able to account for the groundwater flux in your model. And finally, forecast mode. So a good model, obviously, you want to replicate past and measured data, but you want to be able also to forecast, to have an easy way of forecasting with a change of geometry. So obviously, your mine is changing rapidly, your pit is growing, your dumps are growing, and right off the bat, that excludes distributed models and semi-distributed models that are very difficult. Once you set the boundaries, it's really difficult to change the geometry. So that leaves us with lump models. You want to deal with non-stationarity, so the changing land use and climate change. And you want to be able to transfer parameters to ungaged catchments easily. So I found a good model that I'm a big fan of, which I'm presenting today, and it was developed at the National Institute for Agri-Food and Environment Research, and in the Catchment Hydrology Research Group. And that institute is located in Antony, in France, which is a suburb of Paris. And the main focus, obviously, is hydrology, hydrological modeling, management of hydrological extremes, adaptive management under climate change, hydroclimatic modeling in water-scarce region, and ungaged catchment and regionalization. So let's start with the GR4J model, which really stands for Modèle du génie rural à 4 paramètres journaliers in French. So in English would be rural engineering model with 4 parameters daily time steps. And the main publication is right underneath that title. So that model was developed with a comparative study of 38 rainfall runoff models. Some of them are listed here. Over 429 catchments in France, USA, Australia, Ivory Coast, Brazil, and with a different set of climates ranging from semi-arid to tropical humid. It was found that the models using 3 to 5 free parameters. So again, free parameters, those as you change for calibrating your model. So using 3 to 5 free parameters perform equivalently or even better than more complex models. The models with internal reservoir perform much better than empirical black box models, so just a simple formula, which do not include any moisture accounting procedure. And then I've listed, if you go and just Google GR4J, you'll quickly find that it's been used in numerous studies and publications, and it's showing an obvious advantage over other models, and it tends to outperform most commonly used models. And I'm not going to go into all the publications, but I've just listed a few here in different parts of the world. So the GR4J model uses 2 forcing functions, so the precipitation and potential evapotranspiration. I'm just gonna put option later. The precipitation can be rainfall plus snow melt, and we'll go over the snow model a bit later. It has 4 free parameters that you can change for calibration. So the production capacity, which is the depth of the production store. Conceptually, this corresponds to the root zone of a slice of soil where the atmospheric exchanges occur. You have the transfer capacity, which is really the groundwater transfer capacity, which occurs here in that flow chart. That can be negative and positive. So you can have sort of a leaky catchment, or you can have a gaining catchment. The routing capacity, that's the routing store, which really that's the depth of the routing store. And conceptually, that's more like where the interflow or slower flow will occur. So probably more physically related to the geology and soil cover. And you have the lag, which essentially is the time from a rainfall impulse to a peak flow. the model will, the X1 and X2, the production capacity and transfer capacity are the two main parameters that control the mass balance in your model. This is where you're gaining or losing mass through actual evapotranspiration or groundwater transfer. The routing capacity will influence a little bit your groundwater transfer, but routing capacity and the lag mostly influences the shape of the hydrograph. And you have three output variables. In the publications in literature, really we're only talking about net runoff, so the stream flow. But really the model also gives an explicit formulation for your actual evapotranspiration and your groundwater, obviously your groundwater exchange rate, which is important to us. I'll go in more detail when we dive into the GoldSim file. And then the GR4J model doesn't uses, there's no snow processes in that model. So you need to couple that model with a snow accumulation and melt model, which is called semi-neige, neige being snow in French. Again, the publication right underneath the title. And it originates from a comparative study of 7 snowpack models coupled with 4 runoff models over 380 catchments of varying altitudes located in France, Switzerland, Sweden, and Canada. And it was found that some physical processes were basically superfluous from a model efficiency standpoint, and while bringing additional degrees of freedom. So critical temperature threshold, which is a very popular way of partitioning solid and liquid precipitation, was found not to be the greatest way of doing this, and we'll see what that model suggests instead. The effect of seasonally varying degree day melt factor to account for the changes in albedo with decreasing snowpack has overall less impact than the snow cover depletion curves. So there's sort of, yeah, it's sort of competing, two competing each other. So it was decided to keep a single melt factor rather than the seasonally varying one. The energy input to the snowpack from rainfall and water retention within the snowpack was deemed not necessary as the melt at the base of the snowpack. Important to say that semi-neige does not account for glaciated areas. So that snow model is separated in 5 elevation zones. So important to say they're not 5 equally 5 zones of equal elevation. They're equal area. So it's each zone represents 20% of the total acreage of your catchment. And that's because if you look at a typical elevation area curve for a valley, mountain valley, your last piece in the high peaks has comparatively really small area. So it's a bit irrelevant to model that. If it was equal thickness slices, it would be a bit irrelevant. So we're talking about 5 equal area zones. There are 4 forcing functions, so total precipitation, the mean daily temperature, minimum daily, maximum daily temperature. There are 2 free parameters, the degree day melt factor and the snowpack inertia factor, which basically the inertia to warm up. So you need to warm up your snowpack, and that's the way it's, so that inertia. And then 1 output, which I call gross runoff, which is rainfall plus no melt. And then finally, the evapotranspiration model. So that publication there is mostly in French, but in the appendix, there's a bunch of sort of publications in English. I find it a very interesting treatise on evapotranspiration and really informative. So in this PhD thesis, basically, the author compares 27 potential evapotranspiration model assessed, especially for stream flow simulation efficiency, using 4 rainfall runoff models over 308 catchments in, again, France, Australia, and the USA, with climate ranging from dry, temperate to subtropical. I think it's interesting to mention that it was not tested in tropical, mountain, or subarctic polar environments. And although I like that model, in the mountain region, I've found myself that it was probably not the most ideal one. So it's shown that rainfall runoff models are insensitive to the temporal variation of ETO because most of them act as a low-pass filter. So only a seasonal definition of potential evapotranspiration is sufficient. The rainfall runoff models are insensitive to the spatial variation in ETO, so only one weather station is sufficient. Crop cultural factors, which are used in the Penman equation, did not improve model efficiency, and the best performing models are based on temperature and solar radiation. So this is the formula for the potential evapotranspiration model, which only requires a mean daily temperature and the extra atmospheric global radiation. So for that second one, you can get, there's a formula by Morton that only requires the latitude of your site and the Julian day of the year to get that radiation value. So mostly all very easily obtainable data to run your site, to run your model. So in the model, in the GoldSim file I'll be presenting, I'm simulating, sorry, 3 catchments simultaneously. And I wanted to use very different catchments to show that model was indeed powerful. So the first one, catchment number 1, is the North French River, located in northeastern Ontario, Canada. It's pretty large watershed of 6,680 square kilometers, low altitude, and really characterized by pristine forests, undisturbed boreal forests, and extensive wetlands, typical of the Hudson Bay lowlands. The second catchment is a really small one, 49 square kilometers, located in the Jura Plateau in France, which is really a limestone plateau. Moderate altitude, but very rough winters over there. And light anthropization, forest and pastures. And finally, the Fording River in southeastern British Columbia, a mid-sized catchment, 621 square kilometers. It's a high altitude one, ranging from just over 3,000 meters for the peaks, and the outlet is at 1,230 meters above sea level. And it's moderate anthropization with mostly logging, but there's also mining. So most of the operations from Teck is located in the Fording River watershed. So let's go for the GoldSim model. So just a second. Okay. Right off the bat, very sorry, there's no dashboard with that model, but I think it's simple enough. Everything you need to control is in the input data container. The thing you need to know is this model does not accept unscheduled time steps. So maybe Jason can add to that a little bit later, but I think if you want to couple this with your water balance model that may have unscheduled time step, you need to include that model within a container with an internal clock. So it does not, if any unscheduled time step does not impact the runoff model. So let's start with the input data container. Obviously, you have the required data, so precipitation, min temperature, mean, min, and max temperatures. If you go, everything is in vector format. So for one time series element, I already have my 3 time series for catchment 1, 2, and 3. Same goes with temperature. You have your measure flow, which is required to be able to calibrate your model, again, in vector format. The calibration controls, which I'll touch at the end. The watershed fix parameters. So those are the parameters that you don't touch and you don't vary to calibrate your model. Obviously, you can change them from site to site. So latitude, for instance, this is the different latitude for my catchments. The watershed area, the reference elevation is, and I've explained everything in the description. So that's really the elevation of your weather station where the input data are being measured. In hypsometry, this is each catchment is divided in slices of equal area, and this is the elevation of the median elevation of each slices. So catchment 1 is a very low altitude catchment, so I've put 300 meters for all slices. I don't think it's relevant to model this catchment over several elevations, so I just put the same thing. But catchment number 2 and 3 is important, and that's why it's varying. The precipitation gradient and the temperature lapse rate for taking into account the orographic effect. And then the watershed free parameters for optimization. So I've included them in localized container. When you get to use the optimization module in GoldSim, you can't. Well, it's not. You could try to model to optimize different catchments at the same time. Although I really don't recommend it because you're going to get into you probably not going to reach an optimum. So you need to calibrate them separately. And so instead of having to name differently the fixed parameters, I'm just using the same terminology, but including them into a localized container. So the production capacity, transfer capacity, routing capacity, and lag are the 4 free parameters for the GR4J model. Degree factor, snowpack inertia factor, the 2 free parameters for the snow melt, the snow accumulation melt model. And the initial conditions, that's super important, but if you do, sometimes you find yourself having to calibrate and validate a model with a really short time series, in which case you don't really want to lose that time for your model warm-up. So you can change the initial conditions to try to have your model really start at the right point in time. And then that brings us to calibration control. You cannot, obviously, what I said earlier, you cannot calibrate multiple catchments at the same time. So you need to choose one. So this is catchment select. I have 3 catchments, so you have to enter the number for which one of the catchment you want to calibrate. In this case, it's going to be number 3. The begin calibration and end calibration, that's the date. So I want to allow a period for calibrating the model and a period to validate the model. So in this case, we have 8 years of data, and I'm going to choose a period starting from 1995 to 1998. So 3 years over 8 that are going to be used for calibrating the model. The rest will be validation. And then the objective function select. So when we calibrate a model, we often think of the Nash-Sutcliffe efficiency coefficient, but that, which is great, but it puts more weight on peak flows, and which, if flood forecasting is your main objective, then that's great. But if, for instance, you're more interested in water quality, but then maybe low flows are what you're really looking to calibrate well. So I've included 6 functions here. So the Nash-Sutcliffe, on the log of flows, and the Nash-Sutcliffe on the square root of flows, which is sort of halfway between the sort of normal Nash-Sutcliffe and sort of in between. And then the number 4, 5, and 6 is those same efficiency coefficient, but with an error. You want to, minimize the error on the cumulative volume that you're modeling. Because really, in a mine water balance model, replicating an hydrograph is great, but if you're sending water to your tailings facility, in the end of the day, you're really interested in that volume of water. So if you get that sort of systematic bias over time, then you could run into some problem. So those 4, 5, and 6 objective function is really to try to constrain. Obviously, you're going to lose a little bit on your Nash-Sutcliffe coefficient on the validation, but you're going to gain on trying really to match the cumulative volume. So before we go, because I'm earlier presentation today, I left the optimization for the end, but let's go just right. It's not going to take time. So I have a container for the Nash-Sutcliffe, the Nash-Sutcliffe on square root of flows, the Nash-Sutcliffe on the log of flows, and the error. And you can, that's your objective function. So you're choosing which one of the functions you want to use, and you're choosing your catchment. The formula, if you're not familiar with Nash-Sutcliffe efficiency coefficient, it uses the mean of measured flows. So you need to calculate that mean before the model even starts. So that's why I've included a submodel here, which is initiated right at the beginning of the simulation. You're running that submodel, and it calculates the average of measured flows, and then you can compute the Nash-Sutcliffe afterward. So let's go and actually run, well, before. Let's just take a look. The model takes less than 1 second to run, so that's not bad. So that's catchment number 1, North French River. So like I said, it's pretty good fit when you look in red, model in black is measured. It's pretty good fit, but I did really put some weight on, I wanted to really have a cumulative that matches measured. So this is pretty good, and we'll see the validation score after. This is Le Hérisson in France. This is in log scale because I feel we could see better. Again, it's pretty good fit both for the matching the hydrograph and the cumulative, and I can just go and put it in normal scale. And then finally, the Fording River, which is not calibrating, and that's what we're going to do now. I've just put some dummy parameters there, and so to go, we can just go in edit mode, optimization. The objective function is already set on objective function in the optimization container. Your production capacity, it's already set here. You can choose. If I wanted to model catchment number 1, I would go here in catchment number 1 and then choose production capacity. Right now, it's already set on catchment number 3, which is the one I want to calibrate. So I'm not going to do anything. In the early presentation today, I actually went and changed them one by one. A question that came up earlier was which are the values you're using to calibrate? I've put all of this in the description for each element. So you have here upper bound, 2 that's for the lag, I believe. No, transfer capacity. 2.3125 is your upper bound, and lower bound -3. Something you need to keep in mind, the values that you're putting in those 3 parameters. In the model, the production capacity is actually in millimeters. This is not the value in millimeters. When you're going in your model here, the runoff model X1, the production capacity, you're using the exponential of that value. And I think that I've used that from an example on the web. And I think the reason for that is it speeds up the calibration process. So by using the exponential of that value. So if you really want your actual value of your parameter, don't look in don't look in those containers. Go in the GR4J model, in the runoff model, and look at these values here, which have been adjusted. They call it real values versus transferred values. So those are the real values. So let's just run an optimization right now. Let's try to optimize the model. So now it's set on the log, so function number 2, so the log, Nash cliff of the log of flows. So it's going to try to reach an optimum. So while we're waiting for this to calibrate, we're just going to jump to that second window. And we'll go to the potential evapotranspiration model. Here you have the daily global radiation, which is computed with the Julian day of the year and the latitude of your site. So it's a bunch of angles of the sun compared to, like, I'm not gonna go in detail. I'm not gonna go in detail in there, but the reference to Morton's article is there if you fancy this kind of maths. And the equation for the evaporation is here, which is used here. And I'm just gonna run it quickly here. Okay, so I've put the daily potential in red and your actual, which we'll see a bit later, in green. And if you want to know your sort of annualized ETO, ET0, I've put it, which is basically a moving average, so average over the entire sim. That big dip at the beginning, that's just because the model has not warmed up yet. But as you go in time, it's really getting flat, and you can see that, for instance, for my catchment number 1, I have average ETO of 560 something millimeters per year. Moving to the snow model. So the fraction of snow, and we've discussed that a bit earlier, is not using, so I'm not going to use the equations in those little windows because I'm working in matrix format. So in catchments and elevation zones. So sometimes it looks a little bit crowded. So I've put all the equations that you need in a separate container here. So the fraction of the partition of snow and rain, it uses 2 functions. So it was found that below 1500 meters, using the maximum and minimum temperature, daily temperature, which is often readily available in weather records. Obviously if your maximum temperature is below 0, then your 100% has fallen in snow. If your minimum temperature was above 0, then everything fell in rain. In between, you get this function, which is used in that was taken from the model called Hydrotel, which is used for flood forecasting in the province of Quebec in Canada. Above 1500 meters, this function it was not found to be really effective. So we're using the equation developed by the Army Corps of Engineers, and where it seems to be working a bit similarly, where you have 2 threshold temperatures, which is 3 degrees. If your mean daily temperature is above 3 degrees, then all rain. If your mean daily temperature is below -1, then it's all snow, and you get this equation for in between. Once you have partitioned your precipitation, obviously your rain goes straight to gross runoff, and then your snow feeds the snowpack reservoir. And then you go and calculate your snowpack temperature. So the snowpack temperature is really a function of yesterday's snowpack temperature plus today's temperature times the, so I'm not going to say stupid things here. Your snowpack temperatures are really the temperature of snowpack yesterday times the inertia factor plus your mean temperature today times 1 minus the inertia factor. Obviously, if your snowpack is below 0, there's no potential melt. If your snowpack reaches the temperature of 0, then you can initiate your potential melt, which is a function of the degree day factor. But you need to adjust that potential melt with the actual snow coverage. So as your snow coverage diminishes over the spring, comparatively, your actual melt will decrease. So some model used snow depletion curves that are calculated with remote sensing and aerial photographs. This model does it sort of implicitly with what's called a critical snowpack depth. And again, this uses the you need to calculate the critical depth before you run your simulation. So that's why I've included it in a separate submodel. Essentially, it's this part, fraction of snow and rain and snow precipitation, and it calculates your snow precipitation over many years and averages what is my yearly average snow precipitation, and that becomes your critical snowpack depth. And your snow coverage is defined as if your depth of your snowpack is above your critical snowpack depth, then you have 100% snow coverage. As soon as your snowpack goes below your critical depth, then you start to have less than 100%. And finally, you calculate your actual melt based on your snow coverage and the potential snow melt. And you adjust, again, the snowpack. Your actual snow melt goes to the gross runoff. So gross runoff equal rain precipitation plus your actual melt. Again, I'm going fast over this, but all the equations are there and you have the references for the paper and thesis. Then we have the two forcing functions to run the GR4J model. Are we doing on time? Okay, I'm running a bit late. So I've kept the same nomenclature than in the literature if you want to check that model and see references. P, that's your gross runoff. E, that's your potential evapotranspiration. The first thing that happens is interception. So whichever is greater sort of prevails. So if your precipitation is greater than the evapotranspiration, then you're gonna all your evapotranspiration will be satisfied by interception and vice versa. And we're left with the net precipitation and net evapotranspiration. And those two are going to act on the production store, which I mentioned is conceptually the root zone. So you're updating your root zone reservoir with your net precipitation and this is no longer net precip, and this is the precip to the soil and evaporation to the soil, which are a function of the production store itself. Once you update the reservoir, then you can calculate the percolation from that reservoir. Then the percolation goes to PR, which is essentially what we call excess rainfall. So that's the direct runoff and plus whatever percolation from that production store. And this will be routed by two unit hydrograph. X4, which is your lag, is going to be used to define the ordinates for unit hydrograph 1, which is X4, and unit hydrograph 2, which is 2 times X4. Quickly over unit hydrograph. So in the GR4J model, you first define the S-curve equation, which from then, and then you have a bunch of S-curves with a lag of 2, 5, and 10 days. And from these S-curve hydrographs, you derive your unit hydrograph, which is in dash line. And then you use a discrete convolution, which here, that impulse of rainfall, so of rainfall is routed to its own unit hydrograph, and then each pulse is routed, and then you, by doing that summation, you get your net hydrograph. Fortunately, GoldSim, really conveniently, has its own convolution element. So we don't have to go through all that calculation. You just need to enter the S-curve, which is the integral of the transfer function. And it does it for you. One thing very important, I had lots of questions this morning. If excess rainfall is split in two, and you get 90%, which goes to unit hydrograph 1 and 10% to unit hydrograph 2, and that's a split, that's a fixed split. And in the scientific paper, it was explained that initially that was a free parameter and it was allowed to vary, but it did not bring any efficiency, and actually it deteriorated some of the model output. So they decided that split was the one that worked on most examples. Unit hydrograph 2 goes then to sort of direct runoff. That's conceptually your quick flow, and your unit hydrograph 1 will go to the routing store, and conceptually that's your slower flow. Your groundwater exchange rate will be computed based on the level in the routing store. And from the routing store, you have your sort of slower flow, and you add your direct runoff and your slower runoff, and you get your net runoff in millimeters and your total discharge when you multiply by your watershed area. So I'm just going to come back here and stop. I think my calibration here has stabilized. So I'm just going to, yes, close. And then I'm going to copy optimized value to element definition. And I'm going to run that again. And there you go. Now I have my Fording River catchment, which is calibrated for the lower, like recession and low flow periods. Just a reminder that I did calibrate on 3 years. So I think that it's pretty good. I mean, we have the in all cases, the validation period is pretty outstanding. So if you really want I've put that graph here to have your validation scores for 3 catchments. So that's not the calibration, it's really validation. So on catchment number 1, as you can see, the Nash-Sutcliffe square root and log, it's, it could be better. And if I was calibrating the model based on these coefficient uniquely, I tested it, and I'm getting a much better score. But in this case, I forced it to have the same cumulative volume. And in this case, the error is very low. So pretty good score here. And then for the 2 other catchments, I'm getting some pretty good results. So everything is above 0.8 for catchment 2, and only the Nash-Sutcliffe is probably around 0.75. And then you might be interested in your fluxes in the water balance. So I've included that small container here, which really calculates the yearly average of the different fluxes of your hydrological cycle, and displayed here. So catchment number 1, 2, and 3, precipitation, actual evapotranspiration, which, sorry, I did not. Your actual evapotranspiration is defined here, and it's really a sum of the evapotranspiration from the interception and from the production store. So going back, one thing you note here is the groundwater exchange for catchment 1 is 0. And that's because I forced it to 0. And I guess we can conclude that presentation on that I think it's a very, very powerful model, but this is no silver bullet for a lack of understanding of your site. So in this case, catchment 1, knowing a little bit the geography and morphology, I could not get around the fact that groundwater could be from elsewhere. It could be an important input to that catchment. So there's no way that I would calibrate that model with groundwater exchange. So I forced it to 0. And yet, I still have a pretty good calibration. Yeah, a pretty good calibration. So it's important that when you calibrate your model, you use actual information, whether it's from instrumentation or from a more complex 3D model, finite element, groundwater model in your open pit, et cetera, et cetera. If you have eddy covariance instrument on your waste dumps to calculate the actual evapotranspiration, and you need to take that into account and not just have the model calibrated to stream flow only, because then you're going to run into some problems eventually because you're not getting your water balance right. So I've always said, you know, I've always said I'd rather a flow meter than a water balance model. So I think I can conclude on this, and we still have 15 minutes for questions.
All right, thank you, Nicholas. That's great. Thank you. We do have a few questions, and let me see if I can go through them. Let's see. The first question is, how does this model compare with the Canadian VSMB? I'm not familiar with that one. Do you?
VSMB. No, I'm not familiar with that model.
Okay, yeah. Could you, let's see, Shlomo, could you please spell that one out so we can understand what model that is? Okay, so the next one is, is the lag time a parameter or is it an outcome of the model?
No, it's a parameter. Going back to this, in this case, your lag, if I was to calibrate my model with a lag of 2 days, this would be my unit hydrograph. If I was to calibrate my model with a lag time of 10 days, this would be my unit hydrograph. So no, it's a parameter that you calibrate. It's not an outcome.
Great. Okay. Another question is, have you used the snowmelt model for TSFs?
Yes.
And that's just to be clear for everyone, that's a tailings storage facility.
Yeah.
Yeah.
That's the way I'm understanding TSF. Yes, I've used that. Again, you need to take into account. You need to understand your site. So something that happens is your TSF is usually a nice flat surface with absolutely no obstacle for wind. So you may have wind-blown conditions, and you need to keep that in mind. But yes, I did use that on TSF.
Great. Someone was just asking, is this, are all the computations done on a daily basis? I think the answer is yes, but I just want to make sure.
Yes.
Yeah, okay. Oh, and for clarification, VSMB is from University of Calgary. I'll have to look that up. I'm just not familiar with that model.
No, I'm not familiar with it. Just again to mention again, this is a lump model and conceptual model. So I think it's the best way to go on and using a water balance model setting. So it's you can't. I'm not sure about that model from Calgary, if it's a distributed model or a semi-distributed, but usually you can't use those in a mine setting because your catchments are changing, your open pit is growing, your dumps are growing, and the way the mesh works in a semi-distributed and distributed, you can, but I know only one company that does it, and it's still very to its infancy. You can't really change the geometry once you've set up those models. So that's a lump and conceptual models. So lump empirical model would be like the snowmelt runoff model. So a little bit more simple in its formulation. And
okay. Sorry to interrupt you. I didn't want to interrupt you. Keep.
No, 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 no. I was done. I was just that. No, I can. There's so many precipitation runoff model. I don't know them all, and not
Yeah.
that one in particular.
Okay. Well, one question I had, just when I didn't ask this in the morning, and that is, let's say you had this model, incorporated into a larger system model, for example, a mine water balance model. Would you ever see a feedback from um, the main model uh, back to this model? So, for example, would you be maybe not even feedback, but do you ever have you just mentioned something about like the site changing or something. Do you ever have a model where you're simulating some changes over time that then get put into the inputs of this model, or is it typically standalone, kind of working independently?
No, so I think the way it depends because some of the things I've used the model for in a mine water balance setting is, I mean, some of them are proprietary, so I don't feel the liberty to discuss that too much.
Yeah.
But to model the changes over time, I'll typically use a time series, and instead of having my let's say production capacity or your lag fixed over time, you have it obviously fixed for the calibration period, and then you change it over time using a time series or a lookup table um, based on the outcome. Did you know if you know your evapotranspiration is going to change to this value, then you can just play around with the model and say, okay, well, then this is the production capacity I need, so you can change it later on in the model.
Okay. Yeah. Good point.
And you do have a good feedback example is your phreatic surface bouncing back in your open pit after closure. That's a nice feedback loop. In which case, again, you can do some assumptions to simplify that problem.
And sorry, for my ignorance, but can you remind us what did you say phreatic surface?
Yeah,
What
just the piezometric, the ground, the water table.
Okay, okay. Thank you. Um, so another question is somebody's asking about validation on your model. So the difference between calibration and validation. Have you done validation on the model where I'm assuming that is where you're looking at how well it performs to, um, I guess that, let's see, what would be the difference between validation and calibration? Um,
So you calibrate your model on a split. You split your data time series in two, and you're going to use a portion of that data to calibrate your model. But so if I was to use my entire time series to calibrate my model, then it's kind of cheating because I can't say if my model performs well. Sort of, I don't have to explain that eloquently, but you often need to split your data in two, and that's what we're doing here with the and begin calibration and calibration. So if you look in your simulation setting, my simulation goes from 1995 to 2003, but really my calibration starts in at the beginning at 1995, well, stops in 1998. So from 1998 to 2003, my model is not calibrated on that period. It uses the calibration values and see, is my model still performing well? And that's how you assess the performance of the model. So yes, in this case,
mhm.
that's what I'm doing here. So that validation score is not your calibration score as is the one on the validation period.
Okay, okay, yeah, I see. A follow-up question on that is, can you show on the time series where exactly you shift from calibration to validation?
Yeah, that would have been a nice thing to do. Um, So just to make sure here, input data. And calibration is the 30th of September, 1998. So if I go here for catchment number 1, September 1998 would be about, about here. So right here on this side of the screen, this is where I calibrate my model. And on this side of the screen, this is where the validation occurs. So I could have done it in 2 different colors. Like I thought it was probably a bit heavy and but yeah, it's a good point. You can't see it in the graph right now, but yeah, I'm telling you now. It's this part here is calibration. This part is validation.
Great.
And that goes for catchment 2 and catchment 3 as well. So calibration here.
Yeah.
And validation here.
Okay. Great. All right. Let's see. I think that's the end of the questions. Are there any other questions out there? I think I caught all of them. All right. We'll just, if you don't mind, just hang out for a couple more minutes in case anybody else is typing any other questions.
Not a problem.
While we're waiting, I did ask this in the morning. Let's see. Okay, another question. How did you get an initial estimate for lag time?
So I did not get an initial estimate for lag time. I'm not sure I understand that question well. What you can, like, if I go and input data and let's say catchment 2 for a change, you go to lag. So in this model is set up to have the lag from 0. Well, the lag is not 0 because that's going to give you 0.5 days. So 1.5 day lag. So because it's that's the transfer value. So it's going to be exponential of that number plus 0.5. So your minimum lag will be 1.5 days, and your maximum lag will be about 10 days. And that's how the model is set up. So that's your upper and lower bound. When you run an optimization, it goes between these 2 values and changes it, and that's going to change the hydrograph and to obtain the best fit. So there's no initial value to it unless it's meant by this here in the optimization lag. Your initial value here, you're right. If it's that value you're talking about, this is just the initial value for the optimization. So this was based from the Excel solver, and it was found that it was the value to use for a better optimization in Excel. But I'm not sure the difference between the optimization module in GoldSim and Excel. I just kept that value, but I believe you could start with anyone.
And this is, sorry, is this days, the time here? Maybe you already said.
No, it's a transferred value. This is unitless. So again, right. Lag here, and this is just to speed up the calibration. So if you go from that value, we could use the actual values instead, but I had some pretty good results with this. If I go back to my runoff model and go to lag X4, so it's really the exponential of lag plus 0.5 in days. And I think that is to speed up the optimization.
And then I guess you have to round it, because it has to be the nearest day, obviously, because you have a 1 day time step, right? Is that how that works?
Yes, you do. It's doesn't need to be round. Your lag doesn't need to be round, but in your convolution, obviously your lag there's the lag of the model and the so-called lag in your convolution element, and those are integers. So
Okay.
okay, but
Yeah.
no, your lag, it can be can have
It can be a decimal there.
yes, exactly. Thanks.
Uh-huh. Okay. Okay. Um, someone else did just ask, thanks for the presentation. Is the GR4J GoldSim model proprietary or is it publicly available to play with? And I can answer that we are going to post that in our library there. So you will
Yeah,
be.
it's open source. You can go in that institute I mentioned in the PowerPoint presentation on their website, and it's available in a bunch of formats. Yeah, it's especially that one. There's a whole bunch of GR model. There's like GR4H for hour, GR2M for 2 parameters monthly, and there's a whole bunch of them. This one is open source, so yeah, it's going to be on the GoldSim library.
Yeah, great. Yeah, it'll be up there with, in addition to our the video recording of this presentation as well. Okay, and have you it looks like another question. Have you applied the calibration, or have you applied and calibrated the model to very small mine scale catchments, smaller than 49 kilometers squared catchment in France?
No, not in France. I've used that model for small catchments for an open pit, for waste rock dumps, for sort of undisturbed forested catchments of like 2.5 square kilometers with very good results. Obviously, for an open pit, you need a way to monitor your flow. So again, a good flow meter is always better than a model. So a flow meter at your pit sump, and around waste rock dump, you want ditches, collection ponds, pumps, and again, flow meters. And I was able to calibrate that model for all these several catchment size and land uses with very good results.
Um, and does some of this literature talk about all of the locations that it has been used, this model?
Yes.
Someone's asking about
So
that.
here here you have the sort of official peer-reviewed publication in the Journal of Hydrology where that model is presented. That's in English, and again, it's a scientific paper, so it's obviously it's not simplified, but there's not as much information as in the PhD thesis, which link you have here. Obviously, I was not at the free to do a link for a scientific publication because it's there's some fees involved, but the thesis here is available for free, but it's in French. So yeah, so if you speak French, that's really good. I highly recommend that reading. Usually at the end of these theses, you do have some articles that were written in English. Again, yeah, it might still be a good thing to look at.
Yeah,
So
yeah.
yes, in this thesis, you do have a description of all the locations where that model was tested.
Great. Okay, well, we're out of time. If there are more questions coming in, please, you can send them to me, and I can forward them if I need to Nicholas. But right now, I just want to say thank you very much, Nicholas, for taking the time both this morning and this afternoon, doing 2 presentations. That's a lot, and I really appreciate it. And
My pleasure.
yeah, and I think this is a nice model, and I think it will generate a lot of interest and hopefully be useful for people in their various modeling efforts with GoldSim. So with that, we'll go ahead and end this, and hopefully you can get a chance to register for our upcoming webinars. You can see that on our website. So with that, we'll go ahead and close up, and thanks again for joining, and hopefully we'll see you next week.
Thank you, Jason.
Thank
Thank you,
you.
everyone.
All right. Bye.